Yo, Jorm, are you in here? Jorm. What are you doing? Where you at?
Yo, I'm trying to go to bed.
What do you mean?
I'm trying, bro, I'm trying to go to bed.
Oh, my bad. Alright, what's that? Alright, shoot, sorry, dude. Alright, bro. Good night.
Yo, when was that Discrete project due?
Oh, Good afternoon, class. Good afternoon, LT. So for our problem, we've got if A and B are rational and B is not equal to 0 and R is rational, then A plus B times R is irrational. So, proof by contradiction, what does that mean? Suppose not. A and B are rational and B is not equal to 0 and R is irrational, and A plus B times R is rational. And we know that the not of a if statement does not start with if. Thank you, LT. So basically we're going to start off the proof by saying A plus B times R equals C over D, where C and D are integers and D is not equal to 0, because we said up here that A plus B times R is a rational number. So A equals E over F, B equals G over H, E, F, G, and H are all integers, but F and H cannot equal 0, because like we said, A and B are rational numbers. So just by substitution, we can, say that E over F plus G over H times R equals C over D. This is just substitution. So when we rearrange the equation, we get that C over D minus E over F equals B times R. Then what you can do is you can cross multiply, so you'll get C times F over D times F minus D times E over D times F equals B times R. Divide by B, and you get that CF minus DE over DFB equals R. And logically, we can conclude that this numerator portion here, CF minus DE equals some integer, K, where K is an integer because C, F, D, and E are all integers. So we know that because integers when multiplied and integers when subtracted result in another integer, we have an integer. Same thing with the denominator, so D times F times B is going to give you another integer because they're all bound by integer multiplication. So you have some integer K over some integer L equals R, and this is a contradiction because up here we said that R is an irrational number. So therefore A plus B times R is irrational, where A and B are rational and B is not equal to 0 and R is rational.
Okay. So the second proof is going to be done with contraposition. So we're given that if the sum of two real numbers is less than 50, then at least one of the numbers is less than 25. So we're going to prove that by using the contrapositive, which is saying if two real numbers are both greater than or equal to 25, the sum must be greater than or equal to 50. So the proof of this is actually pretty simple once you flip it around. You can suppose that m and n are real numbers and that each of those two are greater than or equal to 25, as was stated in the problem. Thus, you can say that m is equal to 25 plus a and n is equal to 25 plus b for some real numbers a and b that are greater than or equal to 0. So when you add them, you can say m plus n equals a plus 25 plus b plus 25, which simplifies to a plus b plus 50. Because we know a and b are both greater than or equal to 0, we know that a plus b plus 50 is greater than or equal to 50. Thus, m plus n is greater than or equal to 50, as was to be proven. So by proving the contrapositive, we can then say, therefore, if the sum of two real numbers is less than 50, then at least one of the numbers is less than 25, which was the original problem.